Hi, so welcome back. In this lecture, we will continue with our second order linear ODE. We are doing D operator. That's a new method that we have brought in. We've discussed algebra. We've discussed how to implement those properties of algebra to find solutions to differential equations. We've sort of given an example in the last lecture, which was really this example of finding the differential or finding the particular solution of a differential equation when the input was just this, and this was also there in the assignment. We will come to that and we will generalize that result today. So just a small recap of what we had done was that suppose we were solving this differential equation, second order linear ODE. B and C are the constants, real numbers, and we have some general ft, which is the input, okay, on the right hand side. The algebraic structures that we have developed over the last couple of lectures was that we can represent this left hand side by the action of an element of the ring of power series, which I'm calling QD, as the element from the ring of power series R D here. Of course, you have to refer back to all the developments from algebra that we have done. We can represent the left hand side as an action of this QD, where QD is given by this polynomial of degree 2. It really is a power series, but with zero coefficients from the next term onwards. This action of this term on x, which is a function which has to be differentiable, okay, many times, infinitely many times. D here is an indeterminate or a variable, but finally we give it a main meaning. We've said that D acts as the operator, Di acts as the operator, which is the ith differentiation of something that it's an operator, so the function is missing here. So it's the differentiation of whatever function you have to put in here to the order I, okay? So right, so that's what the development was, just representing the left hand side from and turning this left hand side, which is really an expression in analysis, double differentiation and then a one-time differentiation. It's an analysis going on here, okay, but turning that into an algebraic structure, which is the action of a ring element on a group element, where x was an element, x and f the input, they were elements of C infinity, which is the group of all functions which are differentiable infinitely many times. And we said that for certain elements like QD, where C was non-zero, and we're dealing with differential equations where C is not zero. So let's just write that down. We're dealing with differential equations right now where C is not zero, okay? For those kind of expressions, those kind of power series or polynomials, the inverse of that element, this is a ring element, the inverse of that element, the multiplicative inverse, existed. And if we multiplied or if we acted on both sides by that multiplicative inverse, which we call Q inverse D, the left hand side just reduces to X because of all the group multiplication and the ring multiplication that goes on there, and we've again covered all of that. You can go back and check what was happening. Finally, we can write X as an action of this new term, it's again a ring element. It's the inverse of QD. The action of this element on this group element, which is an element from C infinity plus, okay, that's the group. Right, now let's write down let's just recap what was Q inverse D. Q inverse D was a notation from the multiplicative inverse notation, and the notation really was how to denote an inverse, but the actual inverse was 1 over this polynomial here, Okay, that was the actual inverse. And which really is 1 over d squared plus bd plus c. And this, if you turn this into, if you want to look at it as an element of RD, which of course it is an element of RD, but for that you have to express that in terms of coefficients and powers of D, because that's what RD was. And the way you do this, you transform this into this expression by Taylor's theorem, expanded by Taylor's theorem, okay? And I've written that out in the last time as well. You have to differentiate this many times at 0 and then keep multiplying the d squared, d cubed term like that. So you can express it, the 1 by QD, as an expression which makes it belong to RD, okay? Now we've also found that for an expression like this, where B and C were given, we've calculated the first 3, and this was also there in the assignment, where A0 was 1 over C, A1 came out to be minus B over C, and A2 came out to be B minus C squared over C cubed. Those are the 3 things that we already know, and we've done it the last time as well. So let's put all of this together. Let's put this theory to use now and analyze and see the different results we have already seen. We have seen the results with various inputs like exponential inputs, sinusoidal inputs, polynomial inputs, mixed inputs like products. So let's put all of them together in this new light, okay? So the first thing that I'm going to do is, as an example, we did this the last time. When the input is a polynomial of degree 2, we said that we did not need to calculate any term beyond A2, because after all, x was given by the action of this Q inverse D. You can see that the action of the Q inverse D on FT, the input. So this action on F, because F was a second degree polynomial, there was no need to put in d to the power 3, d to the power 4 terms, because they would differentiate this to 0. So it was enough to calculate, to find that x for the last time. So x, what I mean by x is really xp. That is, we are finding the particular solution of this differential equation. That x or xp was given by only calculating up to A2, and we ignored the rest of the terms. And therefore, just putting the values of A0, A1, and A2, they came out to be A0 was with F, so A0 was 1 over C, and A1 was minus B over C. D acts on F by differentiation, D2 acts on F by double differentiation, and that was the end of it. So the general result that we can gather from here is that if the input, if the right hand side is not a second degree polynomial but an nth degree polynomial, okay, then in that case, how much do you have to calculate the A1, A0, A1, A2? How long do you have to calculate? You have to calculate up to AN, because, after that, when you have a d to the power n plus 1, those will act on F and render that 0, so we don't need to go beyond n. So really, this Q inverse D, which has to act on F, has to be calculated up to n, and that would be an, and that would be enough. We don't have to go beyond that if F is an nth degree polynomial. Okay, so that's the first result that we want to put together. Okay, so I just want to say this here. We have been calling particular solution as XP. What we see from here, that XP can be given by Q inverse, the multiplicative inverse of this Q, but really that is 1 over QD. Okay, as the actual term, it's 1 over QD before we can expand it out in Taylor's theorem, and that acts on FT. So, instead of calling particular solutions xp, I can just replace that and call it by this expression here, okay? This qd, remember, is the ring element of this ring, and 1 over d is really the inverse of q, or this element, the multiplicative inverse. And this, even though it looks like 1 over qd, it's the actual expression of it is like this. So it's an element of the ring which is acting on f, and we have defined what the action is. So instead of continuing to call particular solutions by the name xp, we can just replace the name, or we can sometimes use them interchangeably. We can just call them 1 over qd ft. Okay, that's a thing that we would be doing from now on. Okay, all right, so whenever you see an expression like this, it would mean the particular solution of this differential equation, where qd is this. Okay, all right, so and that's the first thing that we've learned here. Okay, if the input is up to is a polynomial of degree n, we expand this 1 over qd up to the nth value an, and then just make it act on f, and you would have your answer. You would have your particular solution. Okay, all right. What would happen if I take another one? Okay, I'm rubbing it out because I want to keep this conclusion from the last time here, just for our reference. Let's do another one. Let's do when the input is an exponential solution or exponential function. Okay, e to the power at. This is something that we had done before. Okay, and we knew what the answer was. Let's just write down what the answer was. The particular solution was given by e to the power at, and this was divided by, well, replacing wherever there were x double prime, we had this a square there, and then x prime was replaced by a, and this was just c. Okay, so this was the particular solution when the input was e to the power at, and of course this was the case when this a was not a root of this equation, this quadratic equation. If a was a root of this quadratic equation, that was the case of resonance, and we worked that out with the help of L'Hopital's rule, and we got t e to the power at, and then a differentiation, so 2a plus b. We can tackle those cases by the use of L'Hopital, but really when a is not a root, this was the particular solution. Okay, so let's see how we can match this with what the algebraic structures that we have given to it. Okay, so with this development, xp would be given by the 1 over qd is, of course, this is fixed here. Okay, 1 over qd of this ft, which is e to the power at. Now 1 over qd expanded like this, of course, gives you terms like this. Okay, it's a power series where the first three are known. We've calculated them. I have not calculated the last beyond that. So let's just write that out. a1d a2d square plus dot dot dot. This acts on e to the power at. What would happen if I just act them just by the definition of action of this ring on an element from C infinity? This is an element. Exponential is an element from C infinity. It is differentiable infinitely many times. What would this be? This would just be, well, let's just do it here. a0 e to the power at. a0 just multiplies it because it's a real number. Then a1 d differentiates it once, so I get a e to the power at. Then I have a2, d2 differentiates it twice, so I get a square e to the power at. and of course this continues. We can write this as, we can take e to the power at common. It's common from all of them, right? So let's write e to the power at, and what I have is a0 plus a1a plus a2a square plus dot dot dot. This goes on. Now what is this? This is, you see, when you had d square like that, it was 1 over this expression, d square plus bd plus c. When d is replaced by a, so this d is replaced by a, d square is replaced by a square, this should be, so this e to the power at is as it is, but this is 1 over just d replaced by a, because that's how we got it from Taylor's theorem. This is the Taylor's expansion of 1 over a square plus ba plus c, and that's what we had from before. And this we found out from our method of undetermined coefficients, but even with this algebraic development by the method of d operator, we can find the particular solution by this thing, okay, all that we've developed, and this is what it is. It's exactly what we found the last time. So that matches. So d operator matches with what we had already learnt. Okay, let's take another one. How about a sinusoidal input? What if you had the input as capital A sine small at plus b? Well, this was there on the assignment, the first problem, second part, and we found that the particular solution was capital A over c minus a square sine at plus b. We've worked this out in that lecture where we solved the problems. This was there. So let's see what happens if can I do this with the d operator method? Well, in that case, the particular solution by the d operator method will be 1 over qd on this input, which is a sine at plus b. Right. 1 over qd is what? It's this, okay? Whatever this is, okay? I'm just writing them in general terms, okay? This is what it is. And we just have to operate the whole thing on this a sine small at, okay? Oh, sorry, we got this, so we got this result when b was 0, okay? I think that's important to understand. So we were doing this, so we have to check the result. This was the particular solution when the b was 0, okay? So that you have to check, okay? Yeah, let's just write this out, okay? With x double prime, I don't want the b, okay? So really qd here is just d square plus c. I think that's important to understand. So this b is not there. Now 1 over qd, yeah, 1 over qd, this by, this is really 1 over c plus d square, okay? And I think, yeah, this, if you expand this by Taylor's theorem, what you're going to get is, if you take away a c, you will get 1 plus 1 over d square by c. Okay, this here, now Taylor's theorem expansion of 1 over 1 plus alpha is going to be 1 minus alpha plus alpha square minus alpha cube plus, it goes on like this. Okay, so what we are going to get here is, we are going to get 1 over c. This expression, therefore, if you expand this by Taylor's theorem, that's what we want to do, because we want this as an element of Rd. This is just going to be 1 minus, well, replace alpha by d square by c. So you're going to get d square by c plus the alpha square will be d to the 4 by c square minus d to the 6 by c cube plus like that. Okay, right, that's it. This is the one. So what we're going to do here is this. So xp, the particular solution for this one where b is 0 is going to be as is given 1 over qd acting on ft, which is a sine small a t plus b, and that gives you what? That, let's just expand this in this form. 1 over c, I have 1 minus d square by c plus d to the 4 by c square minus d to the 6 by c cube plus it goes on, and then this whole thing acts on, this is what it is. This is the element of Rd, and hence this expression sine small a t plus b. All right, what does this give us? 1 over c is just a real number. You can just multiply this in, there's no problem with that. This acts on, so 1 acts on this by, can I just take the a out, because a is a constant and these are all acting by differentiation really, so I'm just taking that a out. It has no effect on it. So this is just going to be sine small a t plus b, the first action. The second action is going to be minus 1 over c. Well, d square, what does it do? It turns sine into sine, but a negative sign. Okay, so what you get is negative, so that becomes plus. You get sine a t plus b, but of course a will come out twice, so you will get a square over here. Okay, right. What would happen to d4? Okay, well, 1 over c square. Well, again, sine will remain as sine, but so you have sine a t plus b, but is it with a negative? So there will be 2 negatives which will make it positive. So this sign remains what it is, and a will come out 4 times like this. Similarly, this will have a6 c cube sine a t plus b, and this goes on. Okay, right. What's happening here is this. So again, for this one, d to the 6 gets me 3 negative signs, which is a negative sign, and that negative mingles with this negative to give you a positive. So something like that. So what we have here is, now this is common, this whole thing is common. Sine a t plus b is common, so I'll just take that out. So we have a sine a t over c, this plus b, of course. This is common. And what we have in the brackets is 1 plus a square over c plus a to the 4 over c square plus a to the 6 over c cube plus dot dot dot. And again, this, if you knew, this is, I'll just write it somewhere. Let's see, I don't need the heading anymore. 1 over 1 minus alpha by Taylor's expansion would give you 1 plus alpha square plus alpha cube plus this goes on. So that's like this. Okay, and so this is just going to be a sine a t plus b divided by Well, it's just going to be what? It's going to be 1 minus a square by c. Okay, so this alpha, if you replace alpha by a square by c, that's what you get. Alpha square, sorry, this is going to be alpha, alpha square, alpha cube, like that. Okay, so this is going to be a square by c, then the square of it, a to the 4 by c square, then the cube of it, like that. Okay, and of course you have the 1 over c from outside, which you can multiply through, so you get a sine small a t plus b, and then that is divided by c minus a square, which is what we got. Okay, so this was what we had from before by method of undetermined coefficients, but really if you apply all the algebraic developments, you can actually get the same thing from a different perspective, of course, now. Okay, let's just do one more. I don't need this anymore. I think I'll take one more, which is, we've done this one as well. So number 4, if the input is something like this, it's a mixed input, e to the power at v. Okay, it's a product. It's product of an exponential with some function of t. Okay, v is a function of t. We found that xp was given by, the particular solution was given by e to the power at u, where u, we found u from this particular differential equation. I'll just write it down because it's a slightly bigger one. We got it from u, we got from u double prime plus 2a plus b u prime plus a square plus ba plus c equals v. Okay, so this was one of the problems. This was also there in the assignment, and also we've covered this. So if the input is a multiple of exponential, then the particular solution is given in terms of u, e to the power at u, where u will be found from this differential equation, the particular solution of this differential equation. Okay, whatever you find up from this, that will be the solution. Okay, now, well, let's just do this. So if I write out the QD, remember QD? If I write this out, this of course is a second order linear differential equation. So there is an element of the ring of power series acting on this u, which is a function from C infinity, infinitely differentiable function. This should give me v. Remember, and in this equation, QD will be it's going to be d square plus 2a plus b. You see, this is the constant. This is going to be there's going to be a d from here, plus a square plus ba plus c. Right? You see, this will act on this u term by term to give you u double prime, then this with u prime, and then this one with, oh sorry, there has to be a u here. I forgot that u. Right. Now, of course, remember, this is an element of the ring, so all possible laws of multiplication and addition and distribution, they're all going on because this is an element of the ring. So really, for that, and you can check that, so d square with a 2ad and an a square will give me d plus a whole square. This is possible because it's an element of the ring where all the laws of multiplication and addition and the connection between multiplication and addition, which is the distribution, they all hold, okay? And this is true. Then what do we have? Then we have b, which you can take that common from, again, from distribution laws. You can see that b with d and b with a, okay, distribution laws here. And then you have, so all are used, I guess, only c is left. Okay. So the original equation we were solving, I'll just write that. Remember, I rubbed that out from the previous board. The original equation we were solving was with this input, so e to the power atv. And so this equation had PD, for example. Let's say PDX e to the power ATV, where PD was just this, okay? I'll just write it here. PD is, it's going to be d square plus bd plus c. You know, what we were doing before. So, in fact, that time we were calling it QD, now I'm calling it PD, and I'm calling this new one QD, okay? So, this is what we were solving. This equation is PD times, or acting on X to give me this input. And the way I was going to find it was by solving this equation, U from, I'm going to find U from this, put it here. So, U is found from this equation. This equation basically means this equation, and this QD is this. Okay, so now what's the relation between PD and QD? Well, this is simple. You see, this is like this, except that D is replaced by D plus A. Correct? So really, QD is just D replaced by D plus A. That's it. So, what is the particular solution from this differential equation? It is going to be, as I said, 1 over QD acting on V, because from the algebra, from all the algebra we have learned, the particular solution of this differential will be multiplying or acting both sides by the inverse, okay? And we know what this is. What is this? QD is this. So it's 1 over PD plus A acting on V. So that's your UP. This is what we get. So therefore, the particular solution which we had to find, this is the particular solution, is going to be e to the power AT, and UP is given by 1 over PD plus A acting on V. So instead of solving it by solving U from here, okay, it's given by one simple formula as well. I mean, of course, you have to solve it anyway, but it's, rather than breaking this up into two things, it's given by one concise formula where the particular solution is going to be, you just take out the e to the power AT and you act on V by the inverse of PD plus A. Okay, that's another solution. All right. So there are few more left. I'm probably going to put them on the assignment, and that would complete the whole picture. So the one that was left was, what if you had this one, T and V multiplied together, okay? What would happen to this, okay? This would become, and we can, there has to be, we'll probably ask you to prove it in the assignment. This will be T minus, well, if I'm calling this P, it's going to be P prime D over PD, and the whole thing over 1 over PD acting on V. Okay, this would be the result, and probably be on the assignment. There was another one which we omitted while we were doing sinusoidal. We did the case when b was 0. What would happen if b is not 0? Okay, that was another case. We found in the first assignment, problem 1, we found a general expression when the input was, the function was a sine small a t plus b. We found that, but what about finding this in terms of the D operator method? Okay, so I guess these two will be left basically on purpose to put them on the assignment, and that more or less, completes the picture. That is, whatever equations we have solved in terms of all the inputs, the various kinds of inputs that we have considered, all of them can be given a formula in terms of the D operator method, and that just puts the whole subject of solving differential equations with various inputs under one framework, which is working with the D operator method. Okay, and I think this more or less completes what we wanted to speak about in this lecture, and hopefully we'll take things forward in the next lecture. Thank you.